Since we first looked to the heavens, one question has haunted humanity. Are we alone? And what if the answer came not in a message, not in a radio signal beamed across the galaxy, but in something as simple, as fundamental as water? October 2025. The interstellar Comet 3 I/Atlas is doing something that defies everything we know about visitors from other stars. But it's not what it's doing, it's what it's releasing and where it's releasing it. This is a story about impossibility, about chemistry that shouldn't exist, about water appearing where water has no right to be, and about 16 days that might change how we understand the universe. The discovery came quietly at first, the way most revolutions do. NASA's Neil Gorell's Swift Observatory, a space telescope designed to track gamma ray bursts, the most violent explosions in the universe, turned its instruments toward this wanderer from beyond our solar system. Swift's mission wasn't to study comets. It was built to catch the death screams of massive stars billions of light years away. But in the summer of 2025, astronomers redirected its gaze toward something much closer, yet equally mysterious. 3 I/Atlas. The third confirmed interstellar object ever detected passing through our cosmic neighborhood. When the data started streaming back to Earth, something was wrong. Or rather, something was impossibly right. Water. 40 kilograms of it. Every single second. Pouring from the surface of 3 I/Atlas like a fire hose running at full blast. That's 3.5 tons per day. 84 tons per month. Over the weeks since its discovery, hundreds of tons of water have escaped into the void. But numbers alone don't capture the strangeness. It's the location that matters, the distance, the temperature, the sheer impossibility of what was being observed. This comet was at 2.9 astronomical units from the Sun when Swift caught the ultraviolet signature of hydroxyl, the broken remnant of water molecules shattered by solar radiation. To put that in perspective, $2.90 is nearly 3 times the distance between Earth and the Sun out there. It's cold. Profoundly cold. The kind of cold where water doesn't sublimate, where ice stays locked in crystalline stillness, where comets go dormant and silent. But 3 I/Atlas wasn't silent. It was screaming water into space at rates that violated every model, every prediction, every baseline established from centuries of watching comets from our own solar system. The team at Auburn University, led by Dr. Dennis Bodwitz, stared at the spectroscopic data in disbelief. They checked for errors. They recalibrated the instruments. They ran the analysis again and again. The signal was clean, undeniable. The hydroxyl emission lines at 3,085 angstroms were crystal clear. Water was pouring out of this object in quantities that made no physical sense for its distance from the Sun. To understand why this is so profoundly strange, we need to talk about the physics of comets. Comets are time capsules, frozen archives of the early solar system, or in this case, someone else's solar system. They're made of ice and rock and organic compounds, held together in a loose gravitational embrace. When they're far from a star, they're inert, dead, just chunks of frozen material drifting through the dark. But as they approach a star, something magical happens. Solar radiation begins to warm the surface. The ice, exposed to heat for the first time in millions or billions of years, doesn't melt. There's no atmosphere, no pressure to allow liquid water to exist. Instead, it sublimates. It goes directly from solid to gas, skipping the liquid phase entirely. This gas escapes, carrying dust with it, forming the coma, the glowing cloud around the nucleus, and eventually the tail, that iconic streak we associate with comets. But this process has rules. It has thresholds. Inside about 2 astronomical units from the Sun, solar radiation is strong enough to sublimate water ice efficiently. This is the water sublimation zone. Inside this boundary, comets become active. Their surfaces vent gas. They glow. They develop tails. Beyond 2 AU, the heat drops off dramatically. Water ice stays frozen. Comets go quiet. They might release more volatile ices, things like carbon monoxide or carbon dioxide, which sublimate at lower temperatures. But water? Water needs heat. And at $2.90, there simply isn't enough. Except 3I/Atlas didn't get the memo. It's out there, nearly 3 times Earth's distance from the Sun, losing water at a rate comparable to comets that are much, much closer. 40 kilograms per second. To put that in human terms, imagine a fire hose. The kind firefighters use to battle structure fires. That hose, at full pressure, outputs about 40 kilograms of water per second. Now imagine that hose running continuously, day and night, for months. That's what 3I/Atlas is doing. In the cold, in the dark, where it shouldn't be possible. The implications hit the scientific community like a shockwave. This was the first time water had been directly detected in an interstellar comet. The very first time we'd seen the chemical fingerprint of H2O escaping from a visitor born around another star. And it was behaving in ways that didn't match anything in our experience. Let's rewind for a moment and put this in context. 3I/Atlas is the third interstellar object we've ever confirmed. The first was Oumuamua, discovered in 2017. That object was bizarre. Cigar-shaped or possibly pancake-flat, depending on which model you believe. It showed no coma, no tail, no outgassing that we could detect. It was dry, completely dry, but it accelerated as it left the solar system, a non-gravitational boost that suggested something was pushing it. Some researchers proposed outgassing of pure hydrogen, so faint we couldn't see it. Others suggested solar radiation pressure acting on an unusually reflective surface. And a few, most notably Harvard's Dr. Avi Loeb, proposed that it might not be natural at all, that it could be a derelict light sail, a piece of ancient technology drifting through the galaxy. The debate still rages. The second interstellar visitor was 2I/Borisov, discovered in 2019. This one looked like a comet. It had a coma. It had a tail. It outgassed. Spectroscopic analysis showed it was rich in carbon monoxide, with a CO to water ratio much higher than typical solar system comets. It was clearly a comet, but it was chemically distinct. A visitor from a different stellar nursery, carrying the fingerprint of its birth environment. Borisov taught us that interstellar comets could be recognizably comet-like, but with compositions shaped by alien stellar systems. And now, 3I/Atlas, the third visitor, and the strangest yet. It's not dry like Oumuamua. It's not just carbon monoxide rich like Borisov. It's bleeding water. Lots of water. Water that shouldn't be there. Water that defies the script written by its two predecessors. The pattern we thought we were starting to see, that interstellar objects come in wildly different flavors, just became even more complex. If Oumuamua was a mystery and Borisov was a recognizable outlier, then 3I/Atlas is something else entirely. It's a comet that's rewriting the rules as it crosses our solar system. But the strangeness doesn't stop with the water. The James Webb Space Telescope, the most powerful infrared observatory ever built, turned its gaze toward 3I/Atlas in August 2025. Webb's near-infrared spectrograph, an instrument so sensitive it can detect the heat signature of a bumblebee at the distance of the moon, captured the chemical composition of the comet's coma in exquisite detail. What it found added another layer to the mystery. 3I/Atlas is dominated by carbon dioxide, CO2. The ratio of carbon dioxide to water in its coma is 7.6 to 1. For every molecule of water, there are more than 7 molecules of CO2. That ratio is among the highest ever observed in any comet, period. Solar system comets, both long-period visitors from the Oort cloud and short-period Jupiter family comets, typically show CO2 to water ratios around 1 to 1, maybe 2 to 1 in extreme cases. But 7.6 to 1? That's off the charts. It's a composition so unusual that it demands explanation. Webb also detected carbon monoxide, water ice grains, dust, and a tentative signature of carbonyl sulfide, a sulfur-bearing molecule rarely seen in comets. The water ice grains are particularly intriguing. They're small, less than 1 micrometer across. Tiny crystals of ice drifting in the coma, likely ejected from the nucleus by the explosive outgassing of CO2 and CO. And here's where the water story gets even stranger. The Swift Observatory detected hydroxyl, the breakdown product of water, when 3I/Atlas was at $2 Australian and 90 cents. But Webb's infrared observations, taken when the comet was at $3 Australian and 32 cents, found water ice grains in the coma, but very little water vapor directly from the nucleus. The implication is clear. The water isn't sublimating from the surface of the nucleus, at least not in the quantities Swift detected. Instead, those ice grains, ejected by CO2 outgassing, are drifting away from the nucleus. And as they drift, they're exposed to sunlight. Faint, distant sunlight, but sunlight nonetheless. And that sunlight is heating them. Not enough to melt them, but enough to sublimate them. The ice grains are acting like miniature steam vents floating in space, releasing water vapor far from the nucleus. This is called an extended source. It's been observed in a handful of distant solar system comets, but it's rare. And it's never been seen in an interstellar comet before. This extended source model explains part of the mystery. It explains how water can be active at such a large distance from the sun. But it raises new questions. Why is the CO2 to water ratio so high? Why is 3I/Atlas so rich in carbon dioxide compared to solar system comets? The answer might lie in where it formed. Comets are born in protoplanetary disks, the swirling clouds of gas and dust that surround young stars. The temperature profile of that disk determines what ices can condense and where. Water ice condenses relatively close to the star, inside what's called the water-snow line. Carbon dioxide, because it's more volatile, condenses farther out, in the colder regions of the disk. If 3I/Atlas formed in the outer reaches of its parent protoplanetary disk, in a region where CO2 dominated over water, that would explain its unusual chemistry. Alternatively, it could have been exposed to higher levels of radiation than typical solar system comets. Cosmic rays, high-energy particles that flood the galaxy, can alter the surface chemistry of comets over millions of years. They can break down water ice, reducing its abundance relative to more stable molecules like CO2. Either way, the chemistry of 3I/Atlas is telling us something fundamental about the environment in which it formed. It's a message from another star system, written in molecules. But let's get back to the water, because the activity itself is the most shocking part. The Auburn team calculated that to produce 40 kilograms of water per second at $2 Australian and 90 cents, assuming equilibrium sublimation, at least 7.8 square kilometers of the comet's surface must be active. That's a lot. To put it in perspective, we don't know the exact size of 3I/Atlas's nucleus yet. Hubble Space Telescope observations in July 2025 provided the sharpest images to date, allowing astronomers to estimate the nucleus diameter. Current estimates place it somewhere between 440 meters and 5.6 kilometers across. Let's take the middle of that range, say 3 kilometers in diameter. A sphere with a 3-kilometer diameter has a surface area of about 28 square kilometers. If 7.8 square kilometers of that surface is actively venting water, that's 28% of the total surface. Even if we account for the extended source model, where ice grains are doing some of the work, the observations still imply that over 8% of the nucleus's surface is directly active. That's high, very high. Most solar system comets show active areas covering 3 to 5% of their surface, even at peak activity near Perihelion. 3I/Atlas is more than doubling that, and it's doing it while still far from the sun. There's something inside this comet that's switched on. Some process, some heat source, some mechanism we don't fully understand. And that brings us to the theories. Scientists hate unanswered questions. It's in our nature to seek explanations, to build models, to test hypotheses. So when 3I/Atlas started defying the rules, the theorists went to work. Here's what they came up with. Theory 1. Cosmic ray sublimation. Space is not empty. It's filled with high-energy particles, cosmic rays, that originate from supernovae, pulsars, and other violent cosmic events. These particles bombard any object drifting through the interstellar medium. Over millions, even billions of years, this radiation penetrates the surface of a comet, breaking chemical bonds, depositing energy deep within the ice. Some of that energy gets stored in the crystal structure of the ice itself, creating what are called metastable states. When the comet finally enters a stellar system and warms up, even slightly, those metastable states can collapse, releasing the stored energy all at once. This could trigger sublimation of water ice from within the comet, not just from the surface. It's a plausible mechanism. It's been proposed for other distant comets. But does it explain 40 kilograms per second? That's a violent release. That's sustained, continuous activity. Cosmic ray weathering is usually a slow process. It can enhance activity, but can it drive it at this intensity? The jury is still out. Theory 2, cryogenic volcanism. Some ices don't need external heat to explode. Carbon monoxide and carbon dioxide, under the right conditions, can detonate. Here's how it works. As a comet drifts through space, solar radiation, even faint solar radiation, can warm its surface layers. CO and CO2 ice, which sublimate at very low temperatures, begin to turn into gas. But if that gas is trapped beneath a layer of less volatile ice, like water ice, pressure builds. And builds. And builds. Eventually, the pressure exceeds the strength of the overlying material, and it ruptures. The CO or CO2 explodes outward, carrying chunks of water ice with it. This process has been directly observed on Kuiper belt objects, trans-Neptunian comets in the outer solar system. It's real. It's measurable. And it could explain why 3I/Atlas is active so far from the Sun. The CO2 outgassing, confirmed by Webb, could be driving the water release. But again, the numbers are extreme. The sustained rate suggests something more than sporadic eruptions. It suggests a reservoir, a large, pressurized pocket of volatile ice that's continuously venting. That's possible, but it requires specific conditions. A layered structure, trapping mechanisms. It's not a universal explanation. Theory 3, radioactive decay. Every rock, every grain of dust, every comet carries isotopes. Most of those isotopes are stable, but some are not. They decay over time, breaking down into lighter elements and releasing energy in the process. In large enough quantities, radioactive decay can generate significant internal heat. This is the mechanism that keeps Earth's core molten. It's what drives the geology of Jupiter's moon Europa, melting ice beneath its frozen shell and creating a subsurface ocean. Could 3I/Atlas have enough radioactive material in its core to generate heat? Possibly. If it's old enough, and if it formed in an environment rich in certain isotopes like aluminum, 26, or iron, 60, both short-lived radioisotopes produced in supernova explosions, then it could have a warm interior. That warmth could melt subsurface ice, creating pressurized pockets of liquid water that eventually find their way to the surface and vent into space. The math works. The physics is sound. But the evidence is circumstantial. We need direct measurements of heat flux, thermal imaging, or spectroscopic signatures of specific isotopes. We don't have that yet. And then there's the theory no one wants to say out loud. The one that gets mentioned in late-night conversations, in hallways, in the margins of conference papers. What if it's deliberate? What if the water release isn't a natural process at all, but a controlled venting? A signal, a beacon, a way of announcing presence without transmitting radio waves. Think about it. If you're a civilization capable of interstellar travel, or at least capable of sending probes between stars, how do you catch the attention of other civilizations? You could broadcast radio signals, but space is vast and radio signals fade with distance. You could flash lasers, but you'd need to know exactly where to aim. Or you could do something simpler. Something any civilization with telescopes and spectrographs would notice. You could leak water. Water is universal. It's the molecule of life, at least as we understand it. It's recognizable. And leaking water from a comet at a distance where water shouldn't be active, that's anomalous. That's attention-grabbing. That's a signal that says, look at me, I'm not following the rules. No one is claiming this as fact. No one is writing peer-reviewed papers asserting extraterrestrial engineering. But the whispers are there. Because when you strip away all the natural explanations, when you account for cosmic rays and cryogenic volcanism and radioactive decay, and the behavior still doesn't quite fit, You're left with uncomfortable questions. What if? The timing makes all of this even more intense. In 16 days, on October 30th, 2025, at 11:47 Universal Time, 3I/Atlas reaches perihelion. Its closest approach to the Sunday, 1.36 astronomical units, just inside the orbit of Mars. This is the moment of truth. Perihelion is when comets reveal their true nature. The heat, the radiation, the gravitational stress, all of it combines to strip away pretense. If 3I/Atlas is a natural comet, its water release should surge. The rate should increase dramatically, following predictable sublimation curves. The CO2 should spike. The coma should brighten. The tail should grow. We have models for this. We've watched hundreds of solar system comets go through perihelion. We know what to expect. But if 3I/Atlas is something else, if there's a mechanism we don't understand driving its activity, then the behavior might diverge. It might stabilize. It might intensify in ways that don't match the models. It might shut off. Or it might do something we've never seen before. The countdown has begun. 16 days. Every telescope on Earth and in orbit is locked on target. Hubble, James Webb, Swift, the Very Large Telescope in Chile, the Keck Observatory in Hawaii, ground-based spectrographs from Arizona to Australia, every photon, every spectrum, every shift in brightness. All of it is being captured, time-stamped, archived, analyzed. This is one of the most intensive observing campaigns ever directed at a single comet. And the data, when it's all compiled, when the models are run and the theories are tested, will either confirm that 3I/Atlas is an unusually active but ultimately natural comet, or it will open doors we didn't know existed. The European Space Agency's JUICE spacecraft, currently en route to Jupiter, will observe 3I/Atlas in November, just after perihelion. JUICE wasn't designed to study comets. It's a mission to explore Jupiter's icy moons, Europa, Ganymede, and Callisto, searching for subsurface oceans and potential habitable environments. But mission planners realized that JUICE's trajectory would give it a unique vantage point to observe 3I/Atlas in the weeks following perihelion. JUICE will have the best view of anyone, the sharpest instruments, the clearest line of sight. Its cameras, spectrographs, and particle detectors will capture data impossible to obtain from Earth. There's just one catch. JUICE is so far from Earth right now, so deep in its journey toward the outer solar system, that the radio signals carrying its data take hours to arrive. And the data volume is enormous. It will take months to download everything. The observations are being recorded now in November, but we won't see the full dataset until February 2026. For months of waiting, for months of not knowing, the images exist. The spectra are captured. The measurements are in JUICE's memory banks. But they're locked in transmission, crawling across hundreds of millions of kilometers of empty space at the speed of light. It's like watching a mystery unfold in slow motion, knowing the answer has already been written, but remains sealed in an envelope that won't arrive for months. Meanwhile, the orbiters around Mars have already captured their glimpses. On October 3rd, 2025, as 3I/Atlas passed within 19 cents of Mars, about 28 million kilometers, the European Space Agency's Mars Express and ExoMars Trace Gas Orbiter turned their cameras toward the visitor. These spacecraft weren't designed to observe comets either. They're there to study Mars, its atmosphere, its geology, its potential for past or present life. But the flyby was too rare to ignore. Mars Express, which has been orbiting the red planet since 2003, used its high-resolution stereo camera to image 3I/Atlas. ExoMars to Geo, in orbit since 2016, used its Cassis camera, designed to image the Martian surface in exquisite detail to capture the comet. The images came back showing a diffuse white point of light, a faint glow against the black of space, surrounded by a hazy coma. No tail was visible yet, at least not in those images. The comet was still too far from the sun, the dust production too low, the tail too faint to resolve from Mars' orbit. But the coma was there, a cloud of gas and dust, glowing faintly in reflected sunlight and in the ultraviolet emission of hydroxyl radicals. It was quiet, eerie, a ghost slipping past Mars on its way to perihelion. But beneath that quiet glow, 40 kilograms of water per second were bleeding into space.
The scale is hard to grasp. We don't think in kilograms per second. We don't intuitively understand flow rates. So let's make it tangible. 40 kilograms per second. In 1 minute, that's 2,400 kilograms, or 2,4 metric tons. In 1 hour, it's 144 tons. In 1 day, 3,456 tons. In 1 week, over 24,000 tons. Since Swift first detected water activity in late July, 3 Atlas has lost hundreds of thousands of tons of water. And it is not slowing down. The rate is steady. Constant. As if whatever is driving this process has no off switch. As if the reservoir feeding it is enormous, or the mechanism sustaining it is continuous, or both. This reflects what we thought we knew about interstellar comets. When Oumuamua arrived, we thought interstellar objects might be dry, rock, more asteroid-like than comet-like. When Borisov appeared, we realized they could be ick, but with different chemistry, shaped by different stellar environments. Now 3 Atlas is teaching us that interstellar comets can carry water, lots of it, and release it under conditions that violate our solar system's rules. The universe is more diverse than we imagine. The processes that build comets, that shape their compositions, that determine their behavior, are not universal. Every star system writes its own recipe. And when those comets are ejected, when they wander the galaxy for billions of years, they carry those recipes with them. They become messengers. Time capsules. Libraries written in ice and rock and organic molecules.
The age of 3 I/Atlas adds another layer of profound strangeness. Based on its trajectory, its velocity, and models of galactic dynamics, astronomers estimate it could be between 5 and 14 billion years old. Let that sink in. 14 billion years. The universe itself is only 13.8 billion years old. If 3 I/Atlas is on the older end of that range, it formed in the immediate aftermath of the Big Bang, in the first generation of stars, in an era when the galaxy was young and metal-poor, and the chemistry of planet formation was fundamentally different from what we see today. If it's on the younger end, it's still older than the Sun, older than Earth, older than every rock and grain of dust in our solar system. It has been wandering the galaxy since before our world existed. What has it seen? What systems has it passed? What stars has it orbited, if any?
The water it is releasing now, those molecules of gas break apart in the ultraviolet glare of our sun, might be older than life on Earth. They might have frozen in the disk of a star that died billions of years before our sun was born. Preserved in the cold of deep space. Silent. Waiting. Until now.
And what does this mean for the search for life? Water is the key. Everywhere we find it, we find the possibility of biology. If interstellar comets carry water, if they can remain chemically active across light years, across billions of years, then they're not just debris. They're delivery systems. Panspermia, the hypothesis that life spreads between worlds on comets and asteroids, suddenly feels less like science fiction and more like a testable idea. If 3 I/Atlas can carry water from another star system to ours, intact and active, then so can countless others. Thousands of them. Millions. Seeding planets. Delivering organic chemistry. Writing the recipes for life across the galaxy. We've always assumed that life, if it exists elsewhere, would arise independently, each world solving the chemistry of biology in isolation. But what if that's wrong? What if life, or at least its building blocks, spreads? What if comets are the carriers and star systems are the recipients? 3 I/Atlas is forcing us to ask these questions, not because it's carrying life, but because it's carrying water. And where there's water, There's possibility. But we're getting ahead of ourselves. Right now, the task is simpler. Watch, measure, record. In 16 days, 3I/Atlas reaches perihelion. Every spectrum, every photon, every shift in brightness, every change in the water production rate, all of it will be captured. Telescopes around the world are coordinating. Observing schedules are synchronized. Data pipelines are ready. This is science at its best. Collaborative, meticulous, obsessive. When the data is in, when the models are run and the papers are written and the debates begin, we'll know whether this is simply a comet with unusual chemistry, shaped by a different stellar environment, or whether it's something far more significant. Whether it's a natural wonder or a question mark that demands we reconsider what we thought we understood. The universe doesn't bend to our schedule. It doesn't wait for our theories to catch up. But our curiosity is what defines us. We look up, we wonder, we measure. And when something like 3I/Atlas crosses our path, glowing with impossible water, defying the rules we thought were fixed, bleeding molecules into space that shouldn't be there, we don't look away. We can't. Because the answer to the oldest question, are we alone, might not come from a signal beamed across the stars. It might not come from a radio transmission or a laser flash or a message encoded in prime numbers. It might come from water. Simple, ancient, impossible water leaking from a comet that's been wandering the galaxy since before our world existed. And if that's the message, if that's how the universe chooses to speak to us, then it has a sense of poetry we never expected.
De comundum res begum. System days until perihelion. The window is closing. The data is streaming. Humanity is what? Because when the cosmos rewrites the rules, when something crosses the threshold from another star system and refuses to behave, we have two choices. Ignore it, pretend the anomaly does not exist, file it away as unexplained and move on. Or answer it in demand explanations. Build better models. Ask harder questions. And we will never, in the entire history of our species, been good at walking away from a mystery. This is what we do. This is who we are. And 3I/Atlas, with its impossible order and its alien chemistry and its system they condom to truth, is the mystery of the moment. Let's see what it has to teach us.